Okay, so I understand that this talk will be a little bit different than many of the other talks on the webinar series, but think of it as a little bit of a story, and think of it as a little bit of a thought experiment, especially if you're a student and you want to kind of get into some area of study, and you want to, you know that it can be implemented in some sense in software. What are the types of issues and problems that you might encounter along the way and along that journey? And that is exactly what happened with me, as I'll describe in this presentation. This presentation comes in 3 parts. The first part, since I know I have a very young crowd here, there's a little bit of a history that predates 2000. And in order to introduce some very, very important technologies that actually impact what I was trying to do. That'll be wave format and MIDI. And then I'll provide a bit of motivation of what led me to start exploring music representation and trying to do that, in this case, in the programming language Python. And along the way, there are a number of things, important foundational issues that required special attention in formulating in software. And the real surprises that came along as a result of that. I'm not claiming that this is new stuff. I'm just saying that as somebody who tries to build something and you try to do something in software meaningful, that you are going to run into some real surprises and some that are very delightful. And then at the end, I have a section on what are called music transformations. If you're not into music, don't worry about the fundamentals. Don't worry about anything. I'm not going to go into deep music theory and try to explain that. I'm more interested in light presentation of some concepts in music and what it took to implement them in a software environment. This is not so much a shameless recommendation, but actually, if there's anything about this presentation that you find interesting, you want to do, this is the reference point for it. It's a pleasure of mine to know that I actually succeeded in writing a book at the age of 71 to finally have my first publication of major dimensions. So I'll just mention that. So I told you I was going to talk about some ancient history. So the first thing I'm going to talk about is how did we listen to music? How did we transport music? How did we store music? A long time ago, in fact, in my childhood in the 50s, everybody had these LP vinyl records. You've probably seen them around. You may not understand what to do with them, but we had them all over the place. And we basically what it is a performance is captured on grooves in a plastic album, a plastic thing. And so it's like a spiral groove, goes all the way around, and in the course of the sound waves are captured and etched in the plastic. And then a small diamond-headed needle is placed on a rotating platter, and it reproduces the effects of the sound waves, and with appropriate amplification, it came out. And this is the way we listen to music until somebody said, hey, we could do that musical etching in a tape. We could do that. We could put the musical etching in tape, and it's smaller and actually be more mobile. And so from the 60s, in fact, through to the 90s, people, moved their vinyl recordings into tape, or they bought their music all over again. And they put they had this tape collection. It took less room, and that was it. And then finally in the 90s, 2000s, out came these CD-ROMs, and people said, hey, that'd be cool to put our music on that. And so people moved it from tape to CD-ROM, or bought their whole musical collection all over again, and began to wonder, how many times am I going to have to do this? And then sure enough, a little bit later, Steve Jobs came out and said, hey, you could put that whole sound library, you have all your favorite tunes, you can put them on CD, on flash drive, put it on your phone, put it on an iPod. And people went and did that, and their storage rooms got more pieces of hardware in it to store. And then they walked around with their iPads and iPods in their pockets, until we get to today. And I haven't needed to purchase any songs at all. You can subscribe to Spotify, you can subscribe to YouTube, you can see anything you want, almost any time you want, and on demand. And there's no need for all that storage stuff. So over a course of about 70 years, there's been enormous changes as things became more and more condensed, and the sound packaging became more accessible. So let me switch a little bit on this. What was on those grooves on those vinyl records? What was being etched? Well, I'm going to talk about what's called wave format. And wave format is basically saying that when a performance was being done, it was captured. It was captured by sampling the sound that was going on, maybe in several different places, but at least it was captured at least once. It was sampled at a rate of something like 41,500 samples per second. And what a sample is basically some kind of number. I have an X and a Y value, as I show here. The Y value in this case is normalized between 1 and -1. There's several variants of this available that you could read about. And then that was stored away into a file, or stored away, or streamed, or moved in some way. So audio is a discrete sample of recording of a performance. And over time, it's been changed a little bit, in the sense that you got some compression algorithms, and it turned from WAV files to MP3 files, and then to MP4, which is basically MP3 with video, text, and images added to it. Fine. What I have, and Dr. Karim can share this with you in my presentation for any students that are interested. I have the code on a slide for actually simulating a sampling and playing it in Python. It's not a lot of code, but the point is that if you want to play with this type of stuff and produce sounds and play with adding sine waves together, or any other kind of way that you can imagine, it's a nice way to do that. And for the advanced student, I have a little inkling of what you could do with fast Fourier transforms on this, and so it would be an advanced student type of exercise to do. Now I want to kind of switch to a different type of technology that's been around for a very long time. It's very much related to what I just showed you with the WAV files. It's called MIDI, Musical Instrument Digital Interface. I tend to think of it as an assembly language for sound. And it's a protocol that essentially captures what was done by the performers in making the music. It's not exactly a score. It's not like a musical score. It's low-level computer language. I'll give you a sense of how low level it is. This, I'm pointing here to one of the opcodes for MIDI, and this is basically to turn on a note. The opcode for it is 9. The channel, I'll tell you what a channel is in a moment. And then the pitch are basically like you would find in any musical instrument. You know, middle C is C4. I'll talk about that later. That has a value of 60, and C sharp 4 would be 61, and so forth. So that's that. The P, and then the V's is kind of like, think of it as volume, even though they use the word velocity. It's part of the nomenclature of the MIDI protocol. So conceptually, what happens in MIDI is that you have a set of channels. Channels can be thought of as instruments. You take messages like the ones I just showed you, you arrange them in what I like to call a timed array, or basically an array with time stamps on each message. The time is a special type of timing mechanism that MIDI has adopted. And so it's not necessarily seconds or anything like that. It's something else. And so you put the messages on the tracks, you feed the tracks into the channels. And in the end, if you have a real live setup, like a MIDI keyboard, when you strike a key, like if you press a key here, it'll send a note on message to the computer. Computer would take the MIDI message and send it through its channel to an appropriate sound module. What's a sound module? I'll talk about that in a moment, but basically it's a set of samples of some instrument. So like by that, I mean, take a saxophone, and every possible note it can play, its transitions into other notes and all the like are taken into account and stored away. These can be fairly large in memory, but the point is that it instantly kind of gets converted, and then you could make your keyboard sound like a saxophone if that's what you want to do. You can make it sound like anything. So how is it used? Well, an application, and maybe it's an application on your phone, or maybe it's an application on your desktop, whatever it is that's producing MIDI. The current means for producing sound, for the most part, is to use a technology called virtual storage technology, VST. VST is a free technology. You can find it on GitHub. It's produced by Steinberg. And it's basically two parts to it, a VST host and a VST client. Usually you don't have to worry about these things. This is in case you want to get into the nitty-gritty of it all, if you want to look at the code. But VST hosts and VST clients usually are part of a package that comes with the app, or maybe was installed with the operating system. The VST host is sort of a coordinating sound producing entity. So the app produces MIDI instructions, sends it along channels, it goes to the VST host. Now the VST host has hooked up a number of what I previously called sound modules. In this case, I'll call it a VST client. And you can buy these things all over the place. There are tons of them available, these sound samples. East-West is one of my favorites. It has enormous numbers of instruments that you can take, even choirs. Native Instruments is very well known for their sound samples, be it piano or anything else. Vienna Symphonic, Steinberg itself, Spitfire. There are just so many. Some specialize in certain instruments, and you can build up really nice stuff out of it. So the whole thing here is that the VST host sends instructions, gets the MIDI instructions, and then sends it to whatever VST clients have been attached to it, and off comes MIDI. My point that I wanted to make from all of this is that the MIDI technology is focused more on music production. It's not a means of transmitting music. It's meant more to produce and maybe even modify music if you want. I'm kind of going on a limb there, but whereas the wave file or digital audio is deals more with transmission and deals more with streaming. So this is a typical MIDI-based app. It's called Dorico. It's by Steinberg. I'm not endorsing that here. There are many other similar products around by different companies. Comes to mind is Sibelius and Finale, which are competitors. But I wanted to show you that on my desktop screen, I could fill the whole thing up with this score editor. And this is me composing, well, some woodwinds in one of my favorite pieces that I have. And when I ask Dorico to play it back, it sends MIDI instructions to a VST host who has, and I can link in any number of these. I can link in a VST client, in this case from East West, and say, hey, I want one channel to be a violin, one channel to be an oboe, and so forth. And the tracks will map appropriately, and the sound will be produced actually quite nicely. With these professional sound samples, it's very hard to distinguish it from a recording. It's very, very good. So I told you there's a story involved in this and a kind of a growing experience. So let me tell you a little bit about it and why all of a sudden I went into building a kind of a library to represent music. So this is something that I wanted to build. And actually I have built it twice. An interactive MIDI-based shared internet music experience. And what you have here, and I'm not going to go into great gory detail, but what you have here is like 3 people at 3 different places. It could be on their phones, it could be on anything. Having a shared screen, and we're putting together a piece of music. And the music is built out of small snippets of MIDI from popular tunes. And these things got unified by a common harmony. That is, we specify a harmony in a set of keys. We pull in, we don't care what we pull in because we know it's going to be, as it were, normalized to a good sounding common key and a common set of chords. And along the way, people can take the role of playing an instrument for this or acting as the conductor. And as it's playing in real time, make changes to the music, change the pitches, change, not by changing notes, but by exercising some kind of meta control over them, that you're raising the pitch of a melody. So you have various melodies or bass elements of the composition running at the same time. So this was a nice idea. I actually got it to work. It was quite an effort. And what happened was it was too much work. I mean, look at all the components here. I have a user interface component built out of JavaScript, dealing with all sorts of asynchronous messaging. I had to build a server. I built a server out of Java. Then I had a music component in there. I had all sorts of messaging synchronization code. I had to manage a way to keep everybody synchronized. And the UI development, and I had to find the MIDI fragments from my library of input source. I had to build a VST host. I had to do a lot of stuff, and it got overwhelming in the sense that what I really wanted to do, which was really understand how to make good and interesting music and look at whatever transforms I needed to make this work. Very little time for that. It got too absorbed in everything else. And in the meantime, Steinberg decided to deprecate VST2 and go to VST3, so I had to rewrite this. I got most of that rewritten. And at that point I said, you know, but I'm not really going anywhere with this. It's just labor intensive. And so I said, okay, put this aside. Let's talk about what we really should be talking about. What are the conceptual foundations of music representation? Okay, I see that I'm running a little bit late, but let me give you some ideas of what I found along the way of three or four very interesting aspects about doing this. First of all, let's look at what we're dealing with. And again, I want you to understand, I'm trying to build a component that ultimately will allow me to do transformations on music. That's the goal, but I'm starting from scratch. Well, you start with a model of something. Think of what I'm about to tell you here as a software model. And, or maybe think of it as a mathematical model. Maybe it's better to think of it that way. But what you have is a set of 12 entities that I call tones. There are 12 of them, 0 through 11 here. Okay, and 7 of those have letters. I'm not going to give you the rationale why. That's something that came with music theory. I said, okay, there's C and E. There's a tone in between, but I'm going to refer to it only as a modification of the ones around it, C sharp and D flat, 2 names for the same tone. Whoops. This is, okay. Excuse me, I have a mouse problem with dealing with this. So okay, I have 12 tones. And if I were to think of the frequency that's associated with each tone, it's related by this kind of funky equation. The factor 2 to the 12th comes in. So what I'm trying to do here is the so-called equitempered tonal scale. That it's not to be confused with well-tempered. That's slightly different. And in some ways, maybe it doesn't even matter that much. But at least for now, think of it as each tone, whether it's C, the funny one in between, the D. This one, the frequency of this tone is this tone times 2 to the 12th. And you do that 12 times, guess what happens when you get here? Oh, this is double this tone. Okay, so I got 12 of these. Okay, so suppose, and I can double them if I put them side to side with each other. So here's the whole, basically what you find on a piano from A0, where the numbers represent octaves or basically clumps of these tones. And I have 12 of them, I have 8 of them. Part of one down here, and then the beginning of one up here, but everything else is intact. And that's the model. That's all we're going to deal with. And you say, well, that's well and fine. What would I do software-wise with it? Well, for one thing, the primary actors are tone, pitch, and caching. And well, forget the caching. I mentioned that these were the tones, and these are the pitches. A pitch is a tone associated with an octave number. That's important. And I can make those first-class objects. And then there are lots of issues in resolving and counting and stuff like that, but I can vary that in a static class at the very foundation. And so all that design that I showed you in the prior slide can now be munged together as a foundational element called the diatonic foundation. In fact, that's the name of the class that I wrote for it. And also therein lies a number of common algorithms, almost nuisance type of algorithms where you're counting the number of tones between 2 tones or 2 pitches between 2 pitches that you have to do all along. And especially some really natty problems that occur around octave boundaries when you're like C sharp 3 and C4 are the same. And yet that type of thing has to be dealt with. It comes up fairly often in practice, and you have to kind of figure out that stuff. And then the tones, since there's only 12 of them, I can cache those. I don't have to reallocate them when I start doing music. And I could have done the same with pitch. I didn't, but that same sort of caching could have been done. Now, why is all this stuff important? Well, besides providing a foundation to your music framework, it also avoids the type of problems that commonly occur when people go learning music for the first time and the teacher says, you see the white keys, that's the C major scale. You haven't even gotten to scales yet. So conceptually, people are being taught things in the kind of Wild West kind of way, and talking about things in no particular order and getting confused. So this tries to alleviate the confusion. There is a foundation that looks like the C major scale, but it's not. We're going to talk about scales later. Okay. I think I missed one. Okay. The other big surprise was how do we measure time in music? Now, I know somewhere along the line I have musical events like play a note at some time after playing another note and the like. Somehow there's a measurement of time and order that I had to deal with. Now, the two common things that you could do are base it on real or actual time. Well, that's not very good because performances can be varied in all sorts of ways. So you can't say, well, yeah, you play that C4 quarter note at 2 minutes and 36.5 seconds. No, that's not good. You could use the measures and beat time. You could say measure 5, beat 3 is where the note is, but that's not uniform. The problem with that is that you can change the time signature of the music at any point, and have 3 beats for the music and then 4 beats for the music. And so you kind of lose that uniformity. What I wound up doing was something that was actually staring me right in the face, and that is that we talk about notes in note durations in terms of a unit that we don't define. It's called the whole note. The whole note is a unit of 1, half note, a half, quarter, a quarter. And so if you use these types of fractions or rational numbers as a measuring type, then you can say things like, well, okay, the note that I'm pointing to right now, this C4, is a quarter note at position 0. The next one is at position of quarter for a quarter. Oh, this is at this note is a position a half for a 12th. This is a 12th note, believe it or not, because I have this funky triplet notation to it, and so forth and so on. And this gives me the uniformity I want, and a nice number system that I can use to look at and pinpoint where a note is in the relationship to others within a score. And for those who may be interested to look at this from the computer code, which Dr. Karam can point you to when I tell him where it is, it's on GitHub. I created data types called position and duration and a few others. And so position plus duration is another position and so forth and so on. So it has to do a lot with operator overloading. And that was, this is the type of thing I ran into that I thought was beautiful and I didn't see it coming. So the point I want to make about what I call beat time or measures and then actual time is that you can convert one to the other in any case. So if you really want to know this, you can. Algorithms are easy to do, and you can do those conversions. And then the other thing that I learned that was kind of interesting was this whole notion of musical intervals, which is basically saying I have 2 notes, this note and this note. What's their relationship? And in music theory, they say, well, there's this thing called an interval, And you specify an interval with two things. One is a qualitative sound designation. It's major, it's minor, it's, and you have to kind of get used to that, augmented and diminished. And the other thing is that the distance is given by the number of tones, a number of letter changes, rather, the number of letter changes between these things. For example, here you have C, D, and E. That's 3. And this turns out to be a major 3. Okay, so that's kind of confusing. That's crazy. But when you get right down to it and you start analyzing it, you're finding out that all that's really being done is, yes, they are counting the number of letter changes. They're also counting the number of half steps, or number of times you had to apply 2 to the 12th. But basically the number of half steps between them. And so every interval that's mentioned here and here can be represented as a pair of numbers, the number of letter changes between them, between the two notes, and the number of, I'll use the term that's used, half steps between the two notes. When you have that, and you've basically represented intervals. And this was a, kind of an interesting thing for me to observe and see that. I said, well, I can do that. It's very easy to do. You can look at the interval class in the code base and find that that's what it's based on, those two numbers. And a lot of the source code inside the diatonic foundation can help you do the counting that you need to do. Well, given that, what happened was, since an interval is based on two counts, you can actually add them together, you can subtract them. It turns out that P1 acts like 0. You can make negative intervals, which is basically changing your direction on looking at what the two tones are that you're comparing. And all of a sudden you come up with an arithmetic. Well, it's almost formally a mathematical group, almost. It doesn't fully work because it's basically a closure issue. It has nothing to do with, adding. Everything is commutative, everything works out beautifully, but it turned out that you don't have closure, but for the most part, it is practical to use. You do have to catch exceptions, but this was another little discovery that it came along the way that I thought was good. And interval arithmetic can be very useful in furthering to the next thing, which had to do with keys or modality or tonality or whatever you want to call it. So when you're taught a major scale, they said, oh, this is C major. What you do, you go 0, okay, so one full step over, which is 2 half steps, and then a half, then another full step, then a half step, then 1. You start learning patterns like this. I'm sure every music student you ever met says, oh, it's 1, 1, a half, 1, 1, 1, a half, and that's what it is. When I looked closer, I said, they forgot something. Let's see. They forgot the fact that the letter changes were going up by 1 every time. Oh, that gives you 7 tones. That's good. They say, well, okay, it's easy to overlook that. You may not even think it's necessary until you start dealing with pentatonic modalities or modalities and scales that are not 7 tones. So in this case, 5. And pentatonic is commonly used all over the place. You'll find it in pop tunes, you'll find it in classical, you'll find it all over the place. But it's really just, in this case, you have this pattern, but the sub-pattern for the number of letter changes that you had, it's 2 letter changes from E to, you skipped F and then you went to G, and the same here, was important. And I said, oh, okay, so this template, what we often call modality, and when you start it from a particular tone, it's called a tonality. All that is a specification of intervals. When you're doing computer work, it's good to kind of go back to kind of basics and not reinvent something. So instead of inventing some kind of counting system to do scales and tones, then what you do is specify a set of intervals. And that's how you define it. And then you can utilize it to compute scales or anything else you need. So that was another thing. I'm going to skip over the mode. Most of you know what it is in essence. It's basically you have a scale, but you're going to start somewhere in the middle. And so that's what a mode is. And it's important, but it's not worth going on. So let me kind of quickly go through a few of these and see where we end up. As a mathematician, I wanted to know, I think of transformations like in group theory, isomorphisms and homomorphisms and things like that. Basically, what is it that you're trying to do? You're basically trying to convert one thing into another, preserve some semblance of what the original thing was and change some other aspects of it. So that's what I think of as a transform. And if you think of this particular melody, which this is the harmony nomenclature for what's going on here, but I want to change it from C major to G, melodic minor, the original. Whereas now it changed to so that's what I'm after. And the first one that a lot of tools like Dorico and Sibelius have are shift change or key change. This is fairly common. And so this is the one I tackled, and this is what the code looks like for making a change. And I just did an example of it. Like, here's the original. I'll just change the key to F natural minor. Fine. Okay. Internally, what I'm doing is just making a map from a whole, basically from one keyboard to another. It's not that much room to take up that space in the computer, and it works fine. You can apply it to large sections of music like that. This is a different transformation, maybe one you know about, maybe one you don't know, but basically what it is I'm going to flip the melody line over an axis, a horizontal axis. In this case, say F4, X is like some octave. In that case, I want the scale E to map to switch places with G and vice versa, D and A, C and B. There are cases like here where there's no tone in between. This center pitch or Q pitch, I like to call it, may not exist all the time because there is no note there. E and F are neighbors to each other. And so you can do a neighborhood flip like this. So that's just flipping a scale. You go to a note below and above some point. You can also flip it so that you only retain the chromatic distances. Without explaining it too much, what happens is that the distance from E to G is the same as the distance from G to B flat in terms of half steps. And so you get this kind of mapping. Let me give you an example. This is an original melody. I can take it around C5. C5 is right about here. It's right there. So anything below will flip to the top. Very nice. And then I could do it at C5 again, only do the chromatic reflection. And again, this is accomplished by building keyboard to keyboard maps like I did with the other slide, the other last transform. And it provides a different way of looking at what you're doing and using new materials for any type of composition you may have been working on. I have a few more, but I'm going to skip this one. Let's see, this one was. So I'm going to flip around. What do I have? I think it's A flat 4. I flip it, which is kind of a little more obscure, but I'm doing a chromatic reflection. And that's has a really pleasant sound. Notice the radical change in the key signature that comes by doing that. Kind of interesting. Also, I'm not going to play through this one, but what's interesting is that sometimes when you do these types of flips, you go way out of range, and you have to kind of push it back into a reasonable range of sound. And you can use that with the shift. You do an octave shift. So it's a combination of using two transforms. Reshape is really kind of interesting. This comes from. I'm sorry I'm going over a little bit, but let me go through a few more, if you don't mind. Here's a Mozart sonata. If you connect these with lines, you get a kind of an interesting looking graph. And the idea behind this particular transform is you'd like to go from a graph to a fitted curve as a fitting curve for a set of notes. And that's like taking, in this case, minus x squared plus 2x, a curve like this over a range of 0 to 2, which fits in nicely with two-measure system of two whole notes. And you say, well, that's okay. But the problem is that the range, which is between 0 and 1 here, has to be mapped to a set of pitches. For some range of pitches, C4 to C6 here. And that mapping is called a pitch range interpreter. And basically, I'm saying you have to build something like that basically lines up for any value here, I can get a pitch. And we build these sorts of things. This is a chromatic pitch interpreter. I won't go through it, but basically it's mapping 0, 1 to A0 to C8 and gives you details on how to do it. So this should be fun. So here's a sine curve, so 2 pi x over 3. Here's a kind of an anonymous rhythm. Since I'm going to move the notes around, I didn't even bother to make a melody here. I just said. And if I go back, if I can figure out how to go back. Give me a second here. Here it is. So now I'm going to take that and fit it to this curve. And that's with the chromatic pitch interpreter, but it changes if I stay in the scale. Oops, this mouse gives me a problem. The difference is what happened here is that instead of maintaining 4 notes, 3 of them came to the same note and I took the liberty of aligning them together. But it's kind of fun to see that how it works. I think I'm going to skip this one, but this is basically how you would change the harmony underneath the given melody, change the harmony entirely, and then have the melody conform to the new harmony. And it basically has to do with maintaining chord tones as chord tones, scale tones as scale tones, and preserving the contour shape of the piece of music. I'll play this anyway. This is a Mozart piano concerto. No, it isn't. That's not it. No. But if I change the chords around, sounds sort of the same, but it's fine. And I'll quickly end with retrograde. Retrograde is turning your melody backwards. There's a very famous piece of classical music that actually did do that, but I won't belabor this. This is an original melody. If I turn it around backwards, the means for reversing a melody is not that hard to do and is outlined in that book, but the basic thing you have to worry about is tying notes together, and that can get dealt with. The bigger issue is what harmony do you want to go with it. Retrograde is tricky. Retrograde is tricky because you can start this whole thing off. I mean, right here I'm doing them between two measures. You could start off measure, you could end somewhere else, and then it won't fit when you reverse it. But this was kind of nice. This was what? And then you can reverse it. And then I'm just playing around with the chords. And that's it. So there's this notion of dilation where since I'm over time right now, I'm not going to belabor it. The only thing I'm going to say is that one of the things you learn when you play around with things beyond theory is that, yeah, I can change the notes, I can change everything by a factor of 1/2 and 2, but what if I tried factors of like 4/7? And so in this case, I changed the note, a quarter note to a 7th note. None of this really makes sense in music theory, but in standard music theory, but it does make sense in and of itself. And if you start building notes of arbitrary durational values, you'll get yourself in trouble, but you'll also have a lot of fun.